Thank you for hosting me and thank you for coming, for being here tonight. I'm Davide, and today I want to start with a question, a broad one, which has to do with something we do in our everyday life, from when we wake up to when we go to sleep, and even as we dream. Something I'm doing right now while I speak to you, and that I frankly hope you're doing too in trying to figure out whether I make any sense at all. My question may be stated as follows. What is a concept? And I mean it in the most literal possible sense. What kind of procedure do we employ when we take a concept and throw it into the world? To me, concepts are like swords, scissors, or chainsaws, with which we carve reality into pieces in trying to understand it. We decide, for instance, that that is a desk made of, I guess, plastic, and going roughly from there to there, located in a specific spot within this lecture hall. And if on the one hand, there really seems to be something there, right? An object deserving its own name, definition, concept, whatever. On the other, there's nothing natural in the desk concept or in whatever other concept you might think of. They're not something we find out there or discover while looking for the laws of nature. They're not a gift left there by someone, maybe at the beginning of time, for us to dig out and appreciate in 2024. They are a product of human ingenuity, of our creativity, of our imagination. Whenever we use a concept, whenever we voice it, we're enforcing our power onto the world. Almost, if I may, a violence, because we are splitting reality into pieces. But those pieces are not something reality acknowledges. Who decides, for instance, that this is an arm that goes from here to here? And why not from here to here or from here to here? And what about my head? Why doesn't it include something of what's above it? And who on earth decided that there must be some kind of invisible two-dimensional plane cutting kind of right here, metaphorically, and separating a specific object with its own name, description, concept, identity, dignity, we call head, and another one we call neck. And if my head and neck are two distinct objects with their own concepts, why does the air in this room, which is much bigger, seem to us at least, as single thing? When we craft ideas, when we craft concepts, we are more or less tracing closed curves within the universe. We are tracing boundaries, like when you're a kid, right? You are by the seaside, you take a stick, and you draw a big circle around yourself, then you declare to be your kingdom. And then you discriminate. That's your concept, what's inside it and what's outside of it. But those boundaries, those closed lines, those ways of discriminating are once more something the world simply doesn't see, feel, or recognize. Our universe is a single entity, a single object. I know this may be a weird idea, a hard to swallow pill in a sense. So let's try, someone would call it monism, some philosophers, but they're not here. Let's leave them in their department. So let's try to grasp it with a metaphor. Okay, I love metaphors. I try to sneak them in whenever I can. So I suggest you may picture the world as some kind of giant bowl of cookie dough. You know cookie dough? That thing you obtain mixing flour, butter, chocolate chips, butter, sugar, butter, perhaps raisins, a bit of cinnamon, some butter, and maybe a bit of butter to make them, tasty. That thing you should never, ever eat raw, but which we all know is much better raw than baked into proper cookies. Okay. A word is something like that. A big ball of cookie dough with no precise shape, no structure to it. And in that bowl of cookie dough, you have to put every single thing you deem an element of reality. And not in a boring sense, not just stuff that exists right now, but also stuff that will exist or has existed. That's a four-dimensional universe, as us physicists would refer to it. So we start. We start from me and you, simple objects, don't take that personally, and place those into the bowl of cookie dough. And then we take the sandwich I had for lunch, past object, and the one I'll have tomorrow. I like my routines and place them in there. We take the foxes that roam around London at night looking for garbage and put them there. And then we become more creative and take some old battles like the Battle of Vienna and put it in the bowl of cookie dough. That's part of the word. And then we push it even further and take the beginning of time, whatever that thing might have been, and the end of humanity or the end of the universe itself. Reality, though, is not only comprised of material stuff. Whatever you think about abstract entities, let's try to be inclusive and consider them part of reality. So we take mathematical concepts and put them into a bowl of cookie dough. I'm trying to really get this idea through, right? Take our desires and love and dreams and memories and hate, all that, and place it within a big bowl. That's the word. Now, if you've ever baked, it's here, right? I'm holding it right now. If you've ever baked cookies, you know that a bowl of cookie dough is not ready to be baked, right? Before doing that, you need to take some small portions of it and give them a shape, a meaning, a structure. You need some cookie cutters, and then you bake stuff and you get cookies, and it doesn't matter for us today. Our concepts are for the word what cookie cutters are for cookie dough. They allow us to take a portion of reality and give it a shape, give it a meaning, give it a proper boundary. Okay, does the metaphor end here? If so, it's frankly useless. It's just one of those things people put into monologues to make them creative and quirky and for people to remember them like a memory hook, but not real explanatory power. No, let's try to follow it for a couple miles more. I adapt to your units of measurement here. It's really hard for me. And see where it goes. I'm Italian, I'm used to normal units, but let's try to follow it for a couple of miles, whatever that means, and see where it leads us. When you have to buy some cookie cutters, they usually come in boxes. You can either go to an online shop. I don't know whether I can mention any here, so I'll try to, avoid legal consequences, or to a shop, whatever shop sells cookie cutters, I have no idea. And you have a lot of choices, right? You can pick the ones resembling vehicles. You have the ambulance, the police car, the train, the helicopter, which will always end up breaking apart into the oven. I never managed to keep those things together, but it doesn't really matter again today. Then you have the buildings. You have the hospital, you have the fortress, you have the bridge, those things kids like. Then you have my favorite ones, dinosaurs. And here I have to admit, I tried to learn how to pronounce dinosaur names in English, but I failed miserably, so let's skip it. Let's imagine I mentioned all the things, all right? And then you also have the weirdest ones, the ones I'm more interested in, the one resembling fruits and vegetables, which serve some kind of strange purpose, like if someone knew they had to eat veggies, but wanted to eat cookies, so found some kind of middle ground in which they had cookies, like carrot-shaped cookies and stuff like that. Now, does the same apply to concepts? When we want to pick a conceptual framework with which to carve the word into pieces, do we have any kind of choice? Of course we have, otherwise I wouldn't have, followed the metaphor up to this point. And I would guess that there's infinitely many different ways in which we can cut the word into pieces. At least one for every thinking mind that has ever existed. And I'm sure you had this experience, even a specific thinking mind like me or you, but me almost, you in particular, changes the conceptual frameworks many times along the way. Almost every day, that's my perception. More often than I change my glasses, and I tend to lose them quite frequently. So we don't have a unique way to impose our concepts onto the world. And once more, this may come as a strange idea, an unusual one, a weird one, but try to think about it. Most of our arguments, most of our conversations, most of our fights come precisely from us disagreeing on some fundamental definitions of a concept, what peace or war or justice or freedom or merit or value or equity, all of those mean. Like politics is at least 70% people disagreeing on what words actually mean when, brought to reality. But that also applies to more pragmatic and practical settings if you don't like these vague philosophical things. I'm sure you've all been into arguments over whether a specific piece of contemporary art had to actually be regarded as art, or whether chess or boxing, because it's violent, have to be regarded as sports. We all have those conversations all the time, because those arguments are negotiations, like war ones, over where to trace our borders into the world, the ones we mentioned before. So we have many ways of shaping our concepts. That's the point of it when dealing with reality. But there's a specific way I find particularly interesting, like the veggie cookie cutters thing. Let's call them sharp concepts without giving them a more revealing name, not to spoil anything about the end point of this conversation. Let's call them sharp concepts. And instead of telling you anything about them, I'd rather tell you how to employ them, like a tutorial, right? In a few steps, like 4 steps. So first of all, in order to properly use sharp concepts, you have to pick a portion of the universe. Imagine it as some kind of invisible cube or sphere floating here. You just have to choose whatever you like. You have to be quite precise in, writing down where this piece, because it's invisible, so you have to be precise. You cannot see it, literally. So you have to decide what you're interested in, and that's what we usually call a system in science, right? So that's step 1. Then we get to the concepts. Once you have a system and you disregard everything else happening in the universe, you look into it. And at that point, you can cut it into pieces. You can start introducing some concepts to identify objects within your system. You can do that in the way that looks more natural, more useful to you, whatever your objective is. But the thing you have to be careful about is precisely what we mentioned before, the fact that concepts can be ambiguous. So you have to try to minimize the chance of people disagreeing on the meaning of the concepts you introduce. You have to be extremely precise, accurate. You have to spend days and days and days writing proper definitions for your concepts. You have to employ mathematics, higher mathematics, in making them exactly precise in order to communicate what you have in your brain when you think about them, so that then people can communicate. They have to become intersubjective in a way. I wouldn't say objective, that seems a bit too far, but let's say intersubjective. Then if you like to say objective, I leave it to you. Once we've done that, which is a harder task, we'll be tired, so we can get a chair. Let me get a chair and move this backpack. We can get a chair, sit down, because we've done a job, relax a bit, get a drink, whatever you like, a matcha latte or a hot tea, a Coca-Cola, a beer. We have beers there. You sip on your drink because you're tired. That's a good way of sneaking in some water, because otherwise I couldn't have gone forward. And you look at your system. You have your concepts, you have your objects, the one you introduced and identified. And you start looking at them and observing how they behave, whether they stay still, whether they move, whether they attract each other, whether they repel each other, whether they disappear or multiply. For instance, if there's fire, fire will, I hope, disappear at a certain point, while rabbits will multiply quite quickly. And as you observe the objects you identified moving and evolving in time, you start collecting what we call data. So we had a system, now we have concepts, and we end up with data. You write down stuff. You relax a bit, you sip on your drink, you write, you observe, you write, you take some notes, you sip, you observe, you take notes, and you keep on accumulating data. And after a while, something weird happens, because you realize you become able to see the future. You unlock some kind of superpower. I know you all know that we are in an engineering department, but let's construct the storytelling. Allow me to do this. You become able to see the future. You somehow manage to extrapolate from your data how your system is going to behave in the future. In 1 second, in 10 minutes, in a year, in 10 million years, if your maths works. What you got is what we call a model. And you get hyped up because you started from, observing the universe, and then you gained a superpower. So you recover your energy and pick another system. Define your concept, invisible cube, another one. Define your sharp concepts, sit down, sip on a drink, take down data, and then you construct a model. And then you pick another one. Get a system, collect data, I'll skip a few steps, and then you get a model. And then a system and its model, a system and a model, another model, and they all work super fine, because we are in an ideal scenario. They all work super well, and you start piling up models, becoming more and more able to see the future. And after a while, it might take some months, a year, depends on what kind of systems you're working with. You realize the superpower was not really your own merit, except for all the hard work you put into it. It was not you being able to see the future and, predicting how the system would evolve in time. It is systems that share features. They are not independent from one another. They seem to share some underlying structure. They fall into broad groups, right? You might find 10 systems that are more or less the same, perhaps doubled or halved in size, perhaps with a tiny parameter being tuned in a slightly different way, or one is the mirror image of the other, and then you have another group and another one. But they all share some mechanisms, some fundamental mechanisms. It is not you being a superhero. It's the word that is ordered, that follows some fundamental laws. You know Walzer, right? 1, 2, 3, 1, 2, 3. I'm a really bad dancer, but reality never misses a single note, never skips a beat. By observing it, we realize that there's some fundamental, perhaps mathematical structure to it. I will not push it that far. That's what we call natural laws. It is as if by cutting our cookie dough ball into pieces, we managed to gaze at something lying below it, a more fundamental layer. This whole thing is what we call science. And people, this is the weirdest introduction to the scientific method anyone has ever heard. But it was really important for me to go this way because there's a point, right, a step in the scientific method that it is always overlooked when people tell about science to the public, which is the fact that science is 95% a concept-making enterprise. The toughest and more problematic and dangerous and hardest in all those objectives part of the scientific enterprise is producing the useful concepts you need to tackle a particular system. You know, those sharp cookie cutters we talked about before. Now, I'm not one of those people that think of science as something that started with Galileo one afternoon. I mentioned Galileo instead of Bacon because I'm Italian. Galileo an afternoon. And so I have power now, right, to establish my own history. So I try to take advantage of that. don't take democracy seriously. So I don't imagine science as something starting with Galileo sitting down at his desk, looking at his calendar, noticing that, tomorrow there's a football match, tonight I have a dinner, but I have a couple of hours free this afternoon, so let's invent a method to tackle the mysteries of the universe. It's not something like that, right? That's a myth or some kind of constructed identity. Physicists, because it's always a physicist when physicists tell the story, like to tell themselves. I would rather see science as a more spread out construction that probably traces back to the first time people looked at the sky or tried to make sense of fire and thunders and all that. It is clear, though, so I'm one of those people that don't really believe in a rigid scientific revolution, in a sense. But it is true, and I too have to admit, even though I, destroy the structures and the historical constructions we put upon his, I have to admit that between the 16th and the 17th centuries, something must have happened, right? Either something new appeared, or we became much better at doing something we were doing before. That's what people usually refer to as the scientific revolution. So we started accumulating knowledge at an ease and speed never seen before. And I'm living proof of that. Because on the one hand, I spent almost 10 years doing theoretical physics and super weird stuff in theoretical physics. But on the other, I'm diabetic. And what you see in my hand is an insulin pump. And I can also use diabetes as an excuse for having a sore throat now and having to drink. So this tiny object I have in my pocket, first of all, is covered in plastic. And you all know what plastic is, dead dinosaurs or plants that we became petrol and then we convert it into a nice chassis for my insulin pump. Within it, there's electrical circuits. So rocks, we grind it and then filtered and then turned into wires, giving them a structure, and within which electricity flows. And by electricity, I mean thunders, those we mentioned before, but containing a pocket-sized chip battery, which I insert here every couple of days. While on the other side, there's some insulin, synthetic one, not like yours. We engineer bacteria, Escherichia coli or others. Escherichia coli was the first one because people tend to study it a lot for whatever reason. We engineer them to produce human-compatible insulin that really mimics, at this point, yours. And as a cherry on top of it, inside this tiny thing, within its circuits, we inserted, and the term is kind of abused today, but in this case I really have to use it, an artificial intelligence software I had to train to mimic what I would need from an actual biological pancreas. So this is, in all meaning, like in all possible ways, an artificial pancreas. So I owe my life to scientific development. And on top, I also spent 10 years actually doing science. So I'm above and beyond all kind of suspicion when I tell you that science is super cool, but it also has its own problems. And there's many of them we should discuss, political, ethical implications. I will not touch on those. There's a whole department here at UCL, the Science and Technology Department, precisely dealing with that, so try to take a look at what they do. I want to focus on two specific things, and they both have to do with concepts. That's why we needed that long introduction. Scientific controversies, let me mention, we're here in the UK, let me mention Newton versus Leibniz. I tend to pick, because Darwin versus Lamarck is also a cool thing, but I don't know much about it, so I'm a physicist. Let me use Newton versus Leibniz. That scientific controversy was first and foremost a clash between distinct conceptual frameworks. Newton theory that later became the establishment established itself as the functioning theory of classical mechanics, able to predict how springs and penduli and whatever other classical mechanics object you might think of behave, brought with it, was embodied with a whole universe of concepts. And the point is that as soon as Newton managed to win his war against Leibniz, Newtonian concepts leaked from Newton to his peers and then to colleagues in other departments, maybe maths or engineering or chemistry and so on. And then to the whole intellectual world of Great Britain and then the world. And then into pop culture, in literature, now movies, when we talk about modern day science and poetry and theater. And then it reached us. It did just a couple of decades, not much more, one generation or two. And those ideas that were first only within Newton's mind end up being in everyone's mind, being part of a collective understanding of the world. And as they do that, as we learn them from our environment, they slip from the conscious to the unconscious. We stop realizing, right? We forget, in a sense, they were made by people, by Newton in this case, because that's our example, but it applies to any kind of scientific theory in the history of science. We forget they are made by humans. We start thinking they are part of our natural, intuitive way of tackling the world, of understanding the world, of seeing how it works. Take time. Even though our idea of time was kind of shuffled 100 years ago by Einstein, and we'll get there, we all think of time as some kind of universal clock, ticking at the same pace in every point in space, and going from a distant past to a distant future, finite or infinite is not that important. Something like this arrow I have on my arm, right? Well, when we think of time, we never think about the fact that that notion of time is by no means human. It is by no means shared by all human beings ever appeared on planet Earth. That was produced, packed, shipped, and delivered by Newton himself. And then we simply forgot about it. And this, as I said, creates two big problems. The first one is that sometimes conceptual frameworks, which are tools with which we do science, become dull. They are scissors, swords, chainsaws, yada yada. We need to change them. As any other tool, sometimes tools do not work to solve your new problems. Maybe they worked well on your old problems, but they do not work on the new ones, and you need to change them. But if you don't even realize you're employing some tool, some other person made, it's really hard to go there and change it. You first need to dig your tools out, to realize those concepts went into your unconscious. You almost have to go do psychotherapy to get them out and then rediscuss them and see them in a critical way. That's why it took so long to get to special relativity and go beyond the Newtonian physics. That's the whole point, and that's the problem for scientists. Then there's another problem for people like me, people doing science communication to the public. Namely that most of my job is telling people how revolutionary and crazy and marvelous scientific ideas were when first introduced. But if we take them for granted, it's really hard for us to think as people used to think when those ideas were first crafted. So, let's all do a Gedanken experiment, as Germans would say, or a thought experiment, that's just to sound a bit intellectual. That's something physicists do. So, imagine you can open your skull, and please don't do that. I don't want you to die in general, but in particular, while I give a lecture. So imagine you open your skull and place it next to your seat. Just keep it there, not to mix it with others. And one after the other, take out each and every scientific concept you learned in school and in your daily job and listening to science communication. Start from recent stuff, AI technology and how COVID masks and vaccines work, right? Stuff we all learned, scientific facts. Take them out. And then go back and take out all the technology you have encountered, how to use a computer or a telephone, all that. And then biology and zoology, anthropology, ethology, all of that out. Forget about it, and then take out chemistry and medicine and physics and maths and even basic logic, if you can. Try to be as empty as you can, right? Try to make them all visible, and put them aside. Then remember to put them back when we go home. Now, with this perspective, we are ready to discuss one important concept. The one I consider the most important concept in the history of science, that of atom. And when I say atom, I do not refer to chemistry's atoms. You know, those made of protons and neutrons and electrons. You shouldn't know, because you should have removed that from your skull. I'm not talking about those. I'm talking about a more fundamental notion of atoms. Sadly, we need to use the same word for historical reasons. But in ancient Greek, atom is literally that which cannot be divided. A tiny, elementary building block of the universe which possesses no parts. Okay? Whatever the tiny building block might be, it's not so important. The atomic hypothesis, or the atomist perspective on the world, goes more or less as follows. The world is made of atoms, and all you see can be broken down into these tiny pieces that cannot be broken down any further. Now, this is an interesting conjecture. We should then test and try to understand whether it works or not. But I wouldn't say this is enough to be the most important idea in the history of science. So either I'm doing a bit of clickbait, or there's something else to it. And I would say it's the second one. Because remember what we said before about the way in which we think about the world, right? When you think about the way in which you think about the world. We started from a giant ball of cookie dough. We cut that into pieces, selected a system, cut that into pieces, right? And then perhaps took a piece and cut that further in a completely free way. Select a piece and cut it more, and then more, and then more, and then more, and more, and more, making tinier and tinier pieces, finer and finer conceptual grades. And we had no constraint whatsoever, no law to follow, no limit, because that procedure had nothing to do with the physical world. It only had to do with our way of conceptualizing it. We were omnipotent in doing that. Well, the atomist hypothesis tells us that after you keep doing that for a while, you encounter some bits you have no reason to split. It tells you that at a certain point, if it's correct, nature stops you. It's a you shall not pass kind of situation, right? Here, okay, yeah, you had fun splitting the world into pieces. You played, kid, human, yes, but I'm nature. And here, down to the microscopic world, it is not you deciding how to split me. It's me splitting myself into atoms in a specific and, most importantly, unique way. Not split atoms in different ways, as we did with the cookie dough metaphor. Atoms are atoms. In some sense, they carry their own conceptual structure. This is really important, because concepts were something we were making up to make sense of the universe, while here, you find a tiny bit, you find a tiny piece, you find something which actually deserves its own concept. It's a point in which conceptual structures and the word touch. That's unprecedented. That flips it all over. That completely modifies the way in which we thought about the way in which we think about the world. We started in a top-down fashion, found atoms, and now we connect matter and concepts. And from that point, we can do it all over again, in a bottom-up fashion. Instead of splitting the world into objects, we can build objects with our atoms, and from those construct concepts, assembling their conceptual content. This is what the reductionist hypothesis or reductionist research program is about. It was a dramatic shift in the way we think about the world. So atoms are not only a scientific entity, but also a revolution in the way we think about the way we think about the world, a way of understanding science. And where could such a weird idea come from? Many of us would say ancient Greece. but that has to do with our colonial past and, removing all science from the rest of the world. Actually, the first instance of an atomic hypothesis were found in India. There was a guy called Aruni, which we might regard as the first natural philosopher, in a way, like a master of all of us scientists. And he had quite an easy time, because, 800 years before Christ, there were not so many solved scientific problems. So if you got into the job market, it's not like being a PhD now, you got into the job market, and you had a lot of low-hanging fruits to pick, right? And you could more or less tackle any field of inquiry, any problem, and the guy was dramatically prolific. He produced knowledge. Okay, yeah, I was joking about having open questions, which was indeed the case, because those people could really work from here to there and jump from astronomy to astrology, no real difference, and then zoology, and then human ethics, and then, matter and the structure of matter. But among all the things he did, he proposed us an atomist perspective. Now, there's a problem with Aruni, namely that on top of being a smart guy, he was a humble guy. He wrote what he had to write, like he produced what he had to produce. And the problem is that when we refer to ancient philosophy or ancient science, as you want to call it, we need egomaniacs. We need people that love themselves so much that they spend days and days and days writing and rewriting the same exact ideas, kissing the mirror in the morning as they brush their teeth. And those are the people we find in ancient Athens. There's two of them, Leucippus and Democritus. Now, Leucippus was the master. It's always a master and a pupil, always two of them. Leucippus was the master, and honestly, he was kind of like Aruni, a normal guy, just one of the many professors you see around here. But Democritus had a flair for public speaking, for science communication in a way. Democritus managed to get his ideas in some kind of preserved form to us, and that was not easy. You should picture Democritus, and this is 100% fake and rhetorical, as tall, muscular, tanned, with a long beard, wavy hair, like the kind of guy you encounter in a summer vacation that completely spoils your love life for ages, for decades, right? That was what I wanted to. Yeah, thank you. And Democritus not only believed in the atomist perspective, but added two specific features to these atoms. First of all, they came in different kinds, and any kind of atom produced some properties for the objects you could build with those atoms. So, for instance, if you find yourself eating some bitter food, that's because its atoms are spiky. And if you eat something sweet, that's because its atoms are smooth and nice, right? This might sound a bit, out of the blue, but there's something to it. The idea that if you pick a different kind of atom, you get different properties on a macroscopic scale. So we can grant him that. The second thing about his atoms, which is the most problematic one, not the spiky round thing, is that he thought they were eternal, right? They were fundamental, so they had to be eternal, floating into the void. They could not be created, nor destroyed, because otherwise you would have needed something creating or destroying them. They couldn't have been fundamental. That's really important. Try to remember that. Now, from Democritus, the atomist idea passed from hand to hand through those of Plato that gave it a weird geometric vibe, and sadly ended in Aristotle's hands. Aristotle, for those of you who don't know him, that's really weird, is more or less the guy that wrapped up ancient Greek philosophy, managed to get into palaces, become Alexander the Great master and teacher, and he had a nice life and an important intellectual impact. Some regards him as the most important Western philosopher in history. And the problem is that Aristotle didn't really like the atomistic perspective. He believed the world was made of substances, fire, water, like in those movies in which people control elements and make magic. But those things could be divided forever. For Aristotle, it was not logical or reasonable to think about atoms. And sadly, if Aristotle didn't like your ideas, it was really hard to get them through, because he acted as some kind of censor in, the shift from ancient Greek philosophy to medieval, in a way, Christian philosophy in the West. Talking about the West, and we'll move to the rest of the world. Now, Aristotle had a weird life. Aristotle's intellectual impact, he went to the Arab world and then came back and was integrated within Christianity. But for all that time, the atomist perspective hid underground, picked out sometimes, looking what was happening, but the West, at least, was not ready to talk about atoms. Like, Aristotle's impact was too strong. So in order to find some developments, we need to go in this table tennis style, go back to India and encounter another guy, Dharmakirti. Dharmakirti, almost 1400 years ago, like 7th century, current era, something like that. Dharmakirti was a monk. He had a strange life full of wars and slaughters. He really didn't know how to pardon people. Legend goes, as his uncle once mocked him during a lunch, and he decided as a kid to become a monk of another sect and slaughter all the monks of the sect his uncle belonged to. That's a story passed down, and he actually did that. But one of the important things that Dharmakirti did, because he was a prolific philosopher and a sharp thinker, was to bring up the atomist perspective and provide us with a way to conceptualize atoms that can be created or destroyed without needing parts. He imagined a more fundamental substance, right? A diffused substance from which atoms could emerge and in which atoms could disappear, right? Like a sea. And please remember this image, because we're getting there. Now, the history of the atomic hypothesis from this point on becomes super complicated, full of sub-histories and nice things happening, the idea passing from hands to hands. It becomes complicated, and I don't want to keep you all night. We have pizzas being ordered in like 45 minutes, so I'll try to wrap it up quickly. And I suggest we jump to the moment in which atoms come back in modern science and then stay in modern science. So it's 1808, we are in the UK, in a, those professors, like fancy professor's office with nice wood on the walls and a lot of books, and in particular, a fine table with a few ancient tomes open on it. No one, and when I say no one, I mean no one, has ever read those books. They are for visitors to see, that the professor is an important intellectual, so they're just to show. And close, just a few steps to the left, there's a man sitting on his chair in this kind of thinker pose, right? With a wide forehead, thick glasses, massaging his chin. Once again, to be seen from visitors as a smart guy. He was John Dalton. By the way, Dalton was colorblind, one of the first colorblind scientists we know of, because he studied color blindness. So in medical terms, we still refer to color blindness as Daltonism from Dalton. So in case you don't manage to recognize my red t-shirt, you are part of this story. You are like Dalton. Yeah, this was cheap. I mean, but it never goes flat like the smart ones. But this one always allows me to cheer people up. Now, Dalton observed water. At the time, people knew that water was made of two substances, hydrogen and oxygen, we call them now, and they call them at the time, but clearly didn't know about their microscopic composition. But Dalton noticed something, or if I can guess, his students noticed something, as always. You all know what I'm talking about. That if you split water into oxygen and hydrogen, and you weight them, the weight proportion is always the same. And I dare to guess it's 8 times, like the oxygen is 8 times heavier than hydrogen. I guess there's a lot of chemical engineers in here, so please correct me. I'm right? It's like 1 to 16, something like that, because it's 2 of them. Oh, thank you. 10 years of physics, guys. That's how it, that's how I end up. I don't know, like, how much does the proton weigh? Like 1 kilo to something like that. So He noticed that, and he noticed that that applied to any sample of water you could pick. Like you take some ice, you melt it, you do the 1 to 8. You get a glass of water, 1 to 8. You get water from a 1 to 8, and so on and so forth. So he guessed, bringing the atomic idea up again, that that was due precisely to water being made of, he called them hydrogen and oxygen atoms, right? Water atoms, to Dalton, made of hydrogen and oxygen atoms. Now, he couldn't guess the H2O structure, but it was quite close to it. So, after Dalton bringing back this old, fashion of thinking about the world in terms of atoms, a normal lecture on atoms would go on with the periodic table and the successes of chemistry, but one, you all know about the successes of chemistry, and two, I don't know enough about to talk about it. So I'll try to get, plus, okay, people always talk about the periodic table, how it was discovered, that's super interesting, you can refer to them. I would like to take another route, kind of slightly to the side of it. Let's go to 1827. I'm not interested in atoms, right, in protons, not that, but the fundamental building block of the word, whatever that is. 1827, still in the UK, we encounter another guy with a huge beard in a much more chilled or relaxed attitude. That guy is Robert Brown. Robert Brown was a botanist, more or less studying plants, and a botanist's life at the time was easy. You walked through forests, you had a bunch, that is actually the case, a bunch of students or drawers or slaves, we would refer to them now, drawing leaves for you, and then you would combine them into a nice book, sign it, and then you're done. That's your research work. So Robert Brown had a lot of free time, and he got super interested in pollen. So Brown started, for whatever reason, to study how pollen floats in water. So he sprinkled some pollen into a glass of water and observed it. And he noticed that there was nothing special about big pollen pieces floating in water. They were just doing what you would expect from them. And for some reason, it didn't stop. He looked at tinier ones, nothing special, and tinier ones, regular motion, just going back and forth in water, as you would expect. And tinier ones, nothing. And tinier ones, that's dedication. And then tinier and tinier and tinier. And when you got to the tiniest pollen bits, particles, they were moving in a different way. They were following random paths, going up and then down, and then left, and then right, left, so, no. We call that Brownian motion in honor of Robert Brown. A straight motion, then a sudden change, and then a straight motion, a sudden change, something you cannot really predict. And sadly, he opened the question but was not able to solve it. He guessed a few things, conjectured that pollen possesses, coming from biological creatures, some kind of vital substance to it, allowing it to choose where to go. For some reason that didn't apply to bigger pollen particles, not a solid hypothesis. He was not satisfied with it, and he died without knowing how to solve it. And now we skip all the people that tried to tackle the question and get to 1905. 1905, for someone like me, is quite an important year, because it's the debut year of theoretical physics Taylor Swift. A guy, he was 26, he was not even doing physics as a job, he was doing it part-time, he was working at a patent office. It was called Albert Einstein, I don't know if you've heard of him, right? And his first 4 albums or papers, if you like, in 1905, completely shattered the way we understand the physical structure of the world. In the first one, and once more, he was 26 and doing another job. He published his paper on special relativity and flipped the way in which we conceptualize time and space. 1. 2. He took his theory a few months apart, all in 1905. He used this special theory of relativity to derive the super famous E equals mc squared equation, equating mass to energy. Nuclear bombs, nuclear reactors, decide if that's a positive or not. Then And here I really don't know why. I would be super interested in understanding it. He picked up from where Robert Brown left. Okay, we throw out time and space and then mass and energy, and now it is time for the hard problem, pollen. Worked on pollen and solved the Robert Brown's open question. Realized, and this is very strange, that super tiny pollen bits can bump on water molecules sometimes. It's not frequent, but it sometimes happens. And that explains, there's a lot of water molecules in a glass of water, clearly, that's why you pick it. And that explains the random motion. And this is hard for us to understand as an important thing, but at the time, and if you don't believe me, I suggest to take a look at transcripts from conferences, people still were not sure whether atoms, like chemistry's atoms in this case, actually existed or not. Whether they were an element of reality or some mathematical tool to make things work. And that is completely shocking for me, because they had the periodic table kind of figured out, chemistry was pretty advanced, but they were still debating over atoms being just a useful, idea or an actual thing in the world. This is regarded by historians as the first direct evidence of the existence of atoms and molecules in this case. So, third achievement. With the fourth, he kick-started what we now call quantum mechanics, with his paper on the photoelectric effect, in which he conceptualized light as made of tiny discrete packets we call now photons. So quite a good year to be, when New Year proposals, that's the bar you have to set. Now, with quantum mechanics, which intertwines with the atomic hypothesis history, we managed to construct a model of what chemists call atoms up to this day, finally realizing they were not atoms at all. Clearly, we had discovered the electron and so on, but now we had a mathematical model telling us that atoms were actually made of stuff. Protons, neutrons, electrons, the models worked, predicted the right spectra of emission, not so important right now. Then going on, we discovered that protons and neutrons were themselves made of other things, quarks, gluons, photons, all that, holding everything together. The thing is that putting special relativity and quantum mechanics together, physicists became able to construct particle accelerators, either circular or linear, and started discovering more and more of these tiny things like electrons or quarks inside protons and neutrons, what we now call elementary particles, what we should call atoms, but they appropriated the name, so okay, let's leave it to them. Let me just put it there. We should call them atoms, which is way cooler than elementary particle, by the way. But anyway, particles. Tiny things that seem to possess no part, right? As long as something looks like not having any internal structure, we classify it as an elementary particle. And starting to piling them up, we have roughly between 10 and 20 of them. That's theoretical physics, like the level of precision. In our world, there's between 10 and 20 elementary particles, something like that. And maybe more we haven't yet discovered. Now, physicists noticed two strange things about particles, and we are getting to the end of this. The first property is that they can be created or destroyed. Actually, where's the light switch? Where is it? I wanted to do a scenographic thing. I wanted to, show off a bit. Where is it? So imagine I'm switching the lights on and off. Is it here? Yeah. Maybe. There, there's a pulsar. This one? Oh, this is getting embarrassing. Did I switch them on? Yes, sure, okay. Now, yeah, thank you very much. So, I'm switching them. Okay, imagine I switch them on again. So when you switch on a light, this was a complete failure, I should have tested before. When you switch on a light, you are creating light particles. You are creating what we call photons, okay? So particles can be created, and then photons can be absorbed. You heard it a lot of times that why you heat up when you stay in front of the sun. That's the whole point. So particles can be created or destroyed. They are not like Democritus atoms. They are like Dharmakirti's atoms. And the other thing is that particles come in families. You have a bunch of particles, many of them, we call them electrons, for instance, that share the same exact properties, the same mass, the same spin, whatever that is, the same electric charge. They seem to be identical to one another. And that's weird, because if they were fundamental, there would be no reason for them to be identical. Why should they, right? There seems to be quite a striking coincidence for electrons to be all identical to one another if they are really fundamental. Democritus said that they had to be eternal, first of all, and they should have nothing below them if they're actually fundamental. If we get into a room, perhaps Dalton's room, and find two nice books exactly identical to one another, our conjecture is by no means that the two books are randomly, by chance, identical to one another. We conjecture they come from the same author, the same edition, from the same publishing house. So, if all electrons are the same, and that applies to any other kind of particle, there really seems to be something more fundamental. It hints at the existence of a more fundamental layer, forcing them to be as they are, like a blueprint for electrons. So the two problems can be solved with a Dharmakirtian move, with one object, what we call the quantum field. Physicists realize, and this is the last actor I introduce in our speech, in our conversation. Let's call it a conversation. Pretend to be democratic, right? And let's call this a conversation. The quantum field. You should imagine quantum fields as the fundamental layer of reality existing throughout the universe. So they're not tiny objects, and that's the trick. You do not need to split electrons. You need something that exists throughout the universe, like the electromagnetic field, for instance. These big objects are not only what creates and destroys particles, so we got that, a fundamental substance like Dharmakirtis, but are what forces all particles of a specific kind to be identical. So you have one and only electron quantum field. And that quantum field produces electrons, eats electrons up when they did what they had to do, and clearly they inherit their properties from the quantum field. Let me give you a metaphor once more, I like them. Imagine a pond full of water, okay? That's your quantum field. Then you have a pebble and you throw it into the pond. You transfer some energy into the pond through the pebble, right? You get ripples. Those ripples, those local excitations, as we would call them, are your particles. All electrons are ripples over one and only one electron quantum field existing in any point of space and time, at any point of space and time. And that applies also to Higgs bosons and the Higgs field, perhaps to gravitons and the gravitational field, even if we haven't found them yet, but that's not my problem anymore. I'm not a physicist anymore, or whatever, quarks and muons and tauons, and there's a lot of particles out there. So this is more or less the picture of the atomic hypothesis modern theoretical physics provides us with. A bigger container, which we call space-time, filled with a variety of substances we call quantum fields, whose excitations are particles, and that mix together in a rather weird but finely made cocktail. In a sentence, a universe in a cup. Thank you very much. And I guess it's time for pizzas. I don't know if there's an outro to this or...